Okay, friends, today is the Saturday, 8:30 p.m. in the Indian Standard Time. And as usual, we are here for the Saturday Manufacturing Talk. As you know that this is a mega webinar series we started nearly a year back. Today is the penultimate session. And we are so fortunate to have Professor Jian Cao with us today. Professor Jian Cao doesn't need any introduction as such. But still, I'm reading her, the biography, case. Professor Jian Cao is the Cadiz Collins Professor. She has done undergraduates from Shanghai Jiangtong University in 1989, followed by that MS and PhD from MIT in the year 92 and 95 respectively. She specialized in innovative manufacturing process and systems, particularly in the areas of deformation-based processes and laser additive and subtractive manufacturing process. She founded the University Research Center of Manufacturing Science and Innovation at Northwestern, known as NIMSI. She has co-authored over 200 journal articles and 20 papers. Cao is the editor-in-chief of Journal of Material Processing Technology. We all know the standard of Journal of Material Processing Technology in the field of manufacturing. If you publish one paper in JMPT, we feel, very much glad. Professor Cao is an elected member of the National Academy of Engineering, Fellow of American Association of Advancement of Science, ASME, CIRP, and SME. Her major awards include ASME Milton Seesaw Manufacturing Research Medal, SME Gold Medal, DoD Vannevar Bush Faculty Fellowship, Charles Roos Research Memorial Award from ASME, and Pi Tau Sigma Award, SME Frederick W. Taylor Research Medal, ASME Blackwell Machine Tool and Gauge Award, and NSF Career Award. She served as president of the SME North American Manufacturing Research Institute, chair of ASME Manufacturing Engineering Division, and program director at the National Science Foundation. She is a recipient of ASME Dedicated Service Award. Cao serves on the board of directors of SME and EMA board, nation's fastest growing hard tech innovation and manufacturing center. Professor, the Cao with us today, and she'll be talking about the material property control in directed energy deposition, and also have requested her to talk about the, how we can think of publishing papers, research articles in the field of in JMPT. With this, I request Professor Cao to proceed. Yeah.
Thank you very much. I really thank for the opportunity to speak to the talented crowd right here. And as I mentioned to Professor Sayat, that I have been at IIT multiple times on different campuses. So really, really great to have the opportunity to do that. And also I see some friends in the audience already. So thank you. It is my really, really great pleasure to be here. And let me share my screen first. Yeah, for those of you who have known me for a number of years, as you know that my background is in mechanics and control, and also therefore, manufacturing is really a home to combine these different areas together. So I have been working a lot associated with the metal forming, composites forming. And we started this directed energy deposition, which is active manufacturing, a number of years ago, quite a few years ago now. So today, I'm going to focus on this particular one, directed energy deposition, and that particular process. So to start, and I would like to thank, of course, my group members, as well as my co-director of the lab, Professor CoEAMT. Many of you probably also know him as well. And it's a really great kind of, collaboration, because he's extremely good at machining, and I was on forming, and then we connected together to do laser processing. So this is where the direct energy deposition starts to come in. If you look at this, right, the ultimate goal is to have really autonomous process from design to product. So material science people know the PSPP relationship, process, structure, property, performance very well. As a mechanical engineers, in Northwestern, we add, oops, what happened? Can you still, am I still sharing? Yeah, okay. Do you still see my slides?
Yeah.
Okay, somehow it just stopped up right here on my slide. So as mechanical engineering, right, for us, we add the machine component, because we want to be able to control the process well. So we need to understand that. That's why we want to have our own machine and open architecture, so we can tweak and measure every possible part. And then ultimately, you also want to have a design. So here, when we talk about the design, we are really thinking about integrate the design of the product, process, and material together. Okay, and which is really challenge because of computational cost, and this is where the machine learning starts to come into play. So you are going to hear some of that. And then, of course, finally, you need to know how do you qualify and certify the part you made. So overall, when you connect all these things together, it's through the simulation and data. So today I'm going to, give you a glance about, what we have been doing. So for the machine ones, starting with the machine, this is our own homemade DED machine. We call it RP. And basically you have the laser power, and then you have the coaxial nozzles, powder depositions, and then coming in, and then you monitor it with the infrared camera, as well as you have, different hopper, and then we can control the powder flow rate, and also the environmental chamber, so we can also process the materials, probably a little bit more reactive, right? So I'm not going to go through the application of the DED because at this point, I think people probably are pretty well associated with those processes. What's new, actually, the first installation off-site monitor is called high-speed spectrometer. It's the Sigma Lab system, which is right here. That's the first installation for the DED kind of, worldwide. So I'm going to show you something in terms of what this can do. Basically, when you look at the high-speed spectrometer, it is the very high data acquisition. It's 100 kilohertz. And it can measure intensity, and then also two color basically parameters, so you can measure the true temperature. So here, for example, give you a glance about what you can see. So basically, for example, if you want to make it a airfoil, you can see the intensity as well as the melt temperature measurement coming out from the top. And the nice thing about this one is really, the high resolution in terms of both temporal and the spatial resolution. Spatial resolution, you can go down to the 6 micron kind of, fine details. And then combine that with the IR camera, you won't be able to have these kind of 100 kilohertz. So what we are trying to do is to utilize this to understand the process, material properties, as well as try to control that. And the other thing that we have been doing is also understanding how the porosity actually formed in the DED, and meanwhile, so you want to control the porosity. So this is the X-ray imaging, high-speed X-ray imaging, and the frequency here is 80 kilohertz, and you can see because of different density from the powders, fluids, the solids, so you can see the boundary right here, the melt pool. and X-ray is looking here in this direction, the green direction. And then you can see that this is a really, really very violent process, you know, so you can see the powder coming down, flowing out. The porosity was also coming from the powder itself, as well as, you know, so lack of fusion, or, you know, other kind of mechanisms. So I'm not going to talk too much about this, but the key point that is that what we have found in the past is also the solidification rate has also it determines the porosity shape distributions quite significantly. So let me talk about the PSPP part. So I mentioned about the machine. And then when you look at this one, right, we know the thermal history really determines the microstructure and therefore determines the mechanical properties. So here you can see the image, our image, you know, we are making a kind of I call it metal wafer. You can see the internal structures right there. But the key point that we want to do is to see how we can control the properties. Okay, so you have the nozzle coming down the wall, and one of the first work that we have done is basically looking at the R camera, and then you can take out cut the samples from the single wall, right? And also look at the correlation. So that setup is relatively easy, and you can see the temperature readings, right, at different points. As you build up, you know, you can also see that the top ones, which is the red ones, actually has, even though you use the same laser power, but because of the heat accumulation through the build, you're going to have overall higher temperature. So for this one, you know, we actually did 4 different walls, and in collaboration with the DMG Mori, 80 millimeter wall and wide wall, and then also the wide wall with the melt pool control from the top. So here for this one, you are changing the laser power, try to control the melt pool size from looking just from the top. And then you also have the dwell time, you know, certainly try to homogenize the temperature distribution through the build by giving a little bit dwell time after each layer. So you do the tensor test. That's easy. Just take some time. But the key thing that we find out is the following. And that's, you know, just last year published at the Nature about the computational material right here. So basically you have the thermal history, right, from each point. And then also we got the mechanical properties from those tensor tests. Then through various machine learning tool, which details you can read from the paper, what's plotted right here is for each temperature, we separated to about 50-degree interval. So all these are 50-degree intervals, and the y-axis is a relatively importance of that particular time spent at that temperature range influence the mechanical property. So when you look at this, you know, it came out to be actually 2 zoom. This zoom and this zoom, as you can see, has the highest relative importance. And then if you, so this is just through, you know, data analysis, right? But then it actually try to understand what's going on, the physics of this. And the first period right here is very much corresponding to the solidification area. So, you know, as you can see, the numbers are very close. And the second one is actually is also very much close to the standard heat transfer, heat treatment temperature for this material. This is Inconel 718. So it's interesting in the sense that, you know, we know from the previous studies, the solidification range is very critical for certainly, you know, when you think about the grain structure as well as the porosity buildup. But the other interesting thing is also this this zoom that you spend at the lower temperature range, which is actually corresponding to the material microstructure evolution as well. So let me give you a little bit detail to look at the micrograph. And if you look at, for example, this 80 millimeter wall and at different build height, and this is, you know, the micrograph, and then you can look at, I'm just going to show you all of this and then talk about them collectively. So you can see that the spacing, right, of this, you know, this is closer, which is actually corresponding to the higher solidification rate. And then meanwhile, so this actually, you know, the solidification band drives the grain size. And also, therefore, you have much finer microstructure with a 5 seconds drill because you allow the material to cool down much more rapidly, right? The next thing you observed is the difference in the amount of the lava places, actually, which are nucleated during solidification. So that we know that the lava phase is detrimental to tensile strength. So you can observe the difference also in terms of, you know, how the delta phases is coming out from different thermal history. And because these delta phases, this is actually corresponding to the second band that I mentioned to you earlier, because that cut through the lava phases and actually strengthen the material. So, which is why, you know, the second zoom is also very much, you know, affected the mechanical property, right? So knowing that the rest of this is pretty, you know, straightforward, because then we know this critical time zoom is important. So let's see how, you know, we can use that to determine the yield stress as well as the ultimate tensile strength. So you can actually develop the correlation by analyzing, you know, have the strong correlation, which is, you know, the predicted the ultimate tensile strength and yield strength based on these time zoom. Okay, so the next step, what we want to do, as I mentioned, is design. You know, how do we design the process, right? And so the first thing that we know, the thermal history is important. In order to have a better design, we need to be able to predict the thermal history better. And as you know, when you do the DED, every time you make the material at a point, so if you really want to simulate this kind of fine detail at the local, it's very expensive. So first of all, we have developed we call gamma code internally. Basically, it's a thermal code to simulate the DED process. And then so you can see the domino equation right here to look at the thermal behavior of the DED process. And this is actually, if you look at this, it's very much similar to the neural network. So because we have this time dependency, right? So naturally, you will think about to use a recurrent neural network to predict the thermal history behavior. So we use the gated recurrent units over there and to put the laser toolpath. So this was some time ago. This was like 2018, I believe. Yeah, it's right here. So it's almost 4 years ago now. And then when you look at this, basically we use a gamma code, as I mentioned, to train the network so that we predict the thermal history. Right. So the goal is if we can predict this, in a much faster way, then we can use it for control. And then you can see that it predicts pretty well. It's not just predict well, at the beginning, because this the initial 20 seconds we use for training, it's actually reasonably well, even you extrapolate that a little bit. And when, as you know, for neural network, extrapolation is always a danger. The reason it can do well is because I think, first of all, the geometry is much simpler. It's just kind of 2.5D. Therefore, the physics you captured in the first few layers and actually it still exists, right, for the following ones. So you can actually extrapolate a little bit. Now, as I mentioned, this training was kind of on the simple geometry. And therefore, if you want to make something new, like what we try to make it NU, and then you look at the thermal history at 3 different points, for example, and the 2 points are pretty well, the straight one, the curved one. But then the part that we have the N, the transition point, it's not very well. And that's because in terms of the training data, we just don't have this kind of complexity, right? So the next step is how do we generate this to include more general geometry such that we can predict more general kind of, genetic different builds. So when you look at this, and the idea came out with a graph neural network. So if you can think about the graph, it's very much similar with the FEM. And basically, if you have the CAD file, you know the connectivity of different parts of the geometry, right? So we use a graph on top of the RNN I mentioned earlier, and use that to build up the new network. So the training data is, here are the training sets, the green ones, and you can see that, we are trying to get different geometries. Some of this is actually here, there's a whole embedded right there. So it's much more complex than the previous one, just, things that you have seen earlier. And we also try to build, small ones, bigger ones, different sizes. And once you do that, so this is a recent published at in 2022, early this year. And you can see that it predicts now pretty well. So I'm just going to show you. Here is IMSE, the error, and it's very much stable. And the RNN with the graph neural network can predict various different, geometries. So with that, then the next question is, remember what I really want to do is control. So there are 2 parts that I'm going to show you. One is we call it simulation guided process control. So how do we use a simulation to design the process parameters? Here in this case, we look at the laser power. So one way to look at that, as I showed you earlier, that people have been doing is to look at the mel pool from the top using the infrared camera and use the mel pool lens, right size. But as we know that when you build up things, particularly look at the microstructure, which I'm not going to go to the details right here. It's also the mel pool depth matters. So from the simulation, you can get, right, those kind of information, not from the IR camera experiments. So the idea is use a simulation to calculate the mel pool depth, and then use a simulation, when we can use a PI controller, for example, to actively change the laser power. Such that, for example, if it's a constant laser power, if we want to control the mel pool depths over the build with a certain height, you can have, if this is a constant laser power, but if you change it, right, you can make sure the mel pool depth is being kept. Otherwise, if it's just use a constant one, you can see the mel pool is keep increasing. So we implement this, in the experiment after you calculate it. And then, this is not a direct measurement of mel pool depth, but, from the thermal camera, from the edge, because it's a thin wall, you can kind of sense it. You can see that it's controlled pretty well. Now, the now the next point is, okay, let's try to look at our mechanical properties, right? So we build the box, and two sides has a different melt pool depth control, and you can see that clearly the mechanical properties are very different from these two walls. And the other thing interesting is that, remember I talked to you earlier, here is just about the melt pool depths, right? But also remember I tell you earlier that, the second part, which is the cooling stage, is also important. So, so the next step is actually how can we go beyond just melt pool, because the simulation can get more data than that, right? So this is what we call the second part, which is the differentiable manufacturing simulations for design. So here we basically convert our gamma code into the differentiable simulation code, and then link it with the you have this machine learning tool these days we have a lot of differentiable kind of the gradient is coming by free kind of, right? Because the back propagation, they give you the differentiable variables right there. So with this differentiable, you can actually do the active, kind of optimization. So we implement this with the Tai Chi, which is a library, and basically we try different libraries. Some of the common ones, PyTorch, TensorFlow, and we pick the Tai Chi mainly because of the memory usage. It's less and also faster for this particular engineering application, because many of the Tai Chi and TensorFlow are for the graphics, right? Imaging, and for this engineering application, this turns out to be pretty nice. So first, what we did is we tried to actually see how can we control the entire thermal history rather than just the melt pool. So when you look at this, we did a test run. Basically, you see whether it could converge, right? So the story of this is that yes, you can converge. And then when we say, okay, go back to our single wall, and then let's say we want to control this entire, cooling time as well from different points. And you can see that, the laser power has been changed quite, interestingly. And if you, this is it, and then we implement that into our simulation, into our experiments, and you can see that without that kind of laser power, just constant laser power, which is actually corresponding to the thermal reading, temperature reading from these dashed lines. So it's very widespread. And then when we implement this, laser power from the differentiable simulation, you can see that they are much closer to each other. So overall, I would say that this is ultimate goal, and there's still much more work that needs to be done. Obviously, if we want to control different material properties at different locations, either you want to do it much more uniformly, or if you want to have a graded structure, or if you want to put some porosity where you want it, for example, for the bio implants, right? Or do some other applications. There are just so much different things you can do with this. So as I mentioned, one of the things which is really important is also the behavior of the buildup. So I'm just going to quickly go through this in terms of, once you have the porosities, we also check in terms of how can we use the deep learning to predict the plasticity, right? So, and this one was published actually a number of years ago already, 2019, in the PNAS. Basically, yes, the answer is yes. You can use a deep learning tool and train it and then predict for example, let me just show you the result due to the time constraints. Yeah, because it's kind of a little bit older already. So what we could see that, it can capture the yield surface evolution and, without explicitly specify some of those limits, right? So if you can have a different porosity prediction, that you can also predict that. So that's kind of the research part of my talk. So, I would be happy to answer some questions before I go to the second part, which is talking about JMPT.
Yeah, it's a, the Professor Cao, it's a wonderful presentation. I was amazed by seeing the complexity of the work that your team has done. The just one query from the our side, because you are working on the data driven model and the simulation based model for the design of the process and all. So when you talk about the simulation based model, so how do you do it in the real time?
So what
Real
we do
time.
is, yeah, we will do is in the simulation, we actually, you basically, in real time, you have two different kind of control, open loop control and closed loop control. So when we talk about the simulation-based control right now, it's an open loop control for experiments, because basically you calculate, for example, what is the laser power you would need, and then you do the open loop control, kind of going to the experiments and do that, right? Just try to follow the laser power, but you can certainly also close the loop, further, right? And so in some other work that we have been doing is, for example, because we have this fancy kind of, the spectrometer right here. So you can also use that to predict the next layer's temperature, right? And then you can actually change the material, the laser power during the build to work on the next one. So that's why I'm saying this is actually a very rich area. You can, there are many things you can do.
Excellent, excellent. Let us see some of the questions might be there in the chat box. And I'm also requesting the audience, because large number of scholars are there. Also, the faculty members from different institutes are also present. So I request them to put the questions, if any, in the chat box. Yeah.
Yeah. So take your time, maybe I can, get on to the second part, and you can keep thinking about the question for the first part. I don't see the chat box, so maybe if
I
you
can.
can monitor that.
Yeah, yeah, yeah.
Oh,
So,
here's a chat box. I see. Oh,
so
let's
one
see
of the
then.
questions is that how are you calibrating the emissivity of the material for the pyrometer?
Yeah, that's a really good question. So you use a black body to calibrate that, and we also work very closely with NIST, and use that to do our calibration. Yeah, and certainly this is something, yeah, very important point, because emissivity also changes with the temperature, with the surface finish. So actually there's a very active work associated with that.
So, Professor Kao, we can proceed with the next part of your presentation. By the time I request the scholars or the faculty members who are present to present here, they can put their questions in the chat box. Yeah.
Yeah, so there was one question comment saying the two color parameter. So emissivity is calibrated when we say the IR camera, right? So if we use the two color parameter, that is something you don't need the emissivity correction. Absolutely. The key thing is for that one, you can only read it from the top. So you don't have the side view, for at least for our setup right here. Some of the others, if you set up differently, you can try to do that. Mm-hmm. Okay, so yeah, keep feel free to keep coming, the question, and we try to answer it, as I see it. So the next part, what I was trying to talk about is about this Journal of Materials Processing Technology. And so JMPT has been there for quite some time, as you know, and I took over the editorship in 2018, and here's our team. So basically, we mainly cover certainly additive manufacturing, mainly cover machining, joining, laser joining, or some other joining, mechanical joining, non-traditional machining, as well as forming, of course, and also some recent addition is about the casting, and as well as some of the coding. So here's our coding expert. The one thing that we don't do too much is purely, for example, injection molding process, because there are lots of the other journals focusing on, composite, polymer-based. And but the thing is, if it has certain metal components, for example, sometimes you have the composites with the metal matrix composites, for example, it fits. And there are some recent work also we expanded to the silicon-based, like process it, not process-wise, but actually the post-processing. So if you look at the impact factor of the journal that has been really at the increasing trend. So the previous editors, Professor Takaya and Professor Elwood, they really turned the journal around, and since 2018, you can see that it's continuously increasing. So the key thing that I want to say is, what we did recently, actually, we start to publish much more review articles. And because of the pandemic, particularly for manufacturing, you can't get onto the lab. So I see a lot of submissions with review articles coming in, and we start to publish more. For example, 2019, actually, there was no review article published at JMPT. So, and the following are the requirements that I want to do with the review articles, because the review articles can get lots of attentions if it gives a lot of synthesis thought of the field. Therefore, the last bullet is really very important. It must have an extensive vision for the future research directions. And I typically requires about 15% of that is in that way. So what you try to do is synthesize, what people have been talking about. So some of the review articles, what I got is say A did what, B did what, C did what. Each one has one paragraph. It would be great for thesis, but not necessary for a review article. So, so this is what I'm really emphasizing in terms of how do you create this comprehensive analysis of what people do, and also, give out future directions. And if you have any idea, feel free to contact me. And the other thing that I would like to do is to have people from, from different groups, and because that will enrich the thought, right? If you look at what we have published in 2022 already, so we have 5 of them already. And some of these looking at the, very specific crack test methods for steels. Some of them was this dissimilar material joining, alloy design adaptation for additive manufacturing. So if it's just alloy design, it doesn't fit with the JMPT, because we are connecting with the material processing, therefore it needs to connect it with the process. And additive manufacturing certainly connects lots of these things together, right? And also this one is on the sheet metal forming, and this one is on the, mechanistic artificial intelligence for modeling design and for advanced manufacturing processes. So for the 2021, 2020, I'm not going to read it up because you can search them easily and to look at those review articles. And then we also have been doing special issues. Certainly, we did the Professor Mazinik's 100th birthday for Medal for Me, and fortunately, he actually saw this issue came out before he passed away. The other one is joining by For-Me and hybrid additive. There are quite a few on the additive. We just finished this issue, which is artificial intelligence on advanced manufacturing processes. And that's pretty general. And I'm thinking for this year, coming year, probably a more specific area. So I would like to welcome people to propose these. And typically what I would like to do is also to have people from different regions, Asia, Europe, US, coming together to do a special issue, right? So now talking about the individual papers, I will start with the title and the abstract. And because for people who your work needs to be noticed, and the title and abstract is the starting point. So the abstract needs to be concise and really wants to put out as clearly state the fundamental scientific work that this manuscript is about, and really want to attract readers to read further and ultimately, help to get paper cited. It should avoid, because sometimes I feel myself learning more from not to do than from the category to do category, right? So you try to avoid the following things, you give people impression this is just a routine exercise, nothing new. So for example, people would say, I have done 5 different experiments and I changed the process parameter from A, B, C, and something like this, it sounds like just a routine exercise. You really want to tell people, what your goal is and what is a unique approach, right? So, and then sometimes, the abstract could be confusing if you don't define the terms. And then the other thing is the opening of the abstract. You really don't need too much state-of-the-art kind of statements. Because people, if they're interested to read it, they know this kind of field already. So you can go straight, maybe just one sentence, then you just go straight to the meat. And one of my colleagues was saying, you're not writing a murder story, right? So you don't have to keep the answer to the very end, and just go straight forward about your work. So what's new? And there are some, resources on the web. You can take a look at that. And I want to give you some examples. For example, title. This is a very long title when it was submitted to us. You can read it. Applying a soft adapted deformation acceleration to the hot compression of the titanium aluminum, blah, 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 using hot, blah, blah. So the key thing is, applying something to something. It doesn't sound very scientific, right? It's just a very kind of incremental ones. So that doesn't sound very well. And then using a hot, it really just doesn't tell you what to do. So the new title is Accelerate Hot Deformation and Heat Treatment of this for enhanced hot workability and controlled damage, right? It's much shorter, and also give the key. What's new is actually this work was really talking about this. You can do the accelerated ones to reduce the energy consumption, to increase the cycle time. Reduce the cycle time, and also to have a better, workability. So, so you see the point, right? The work was good, the title wasn't good. So And also, the keywords, please do not be too narrowly focused. Now, let me give you an example about the abstract. So the abstract, the first one, is the old version. In this report, this is not a report, okay? If it's a technical report, I will reject this. And the new design concept is utilized in the preparation of the composites coding, blah, 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 used. And a surface, it just doesn't sound very exciting, right? And doesn't talk about what's new. So the new one says a new hybrid processes consisting of, because what's new, that's new, right? You have the laser processing, nanoparticle, and then the laser, why you want to do this? You say laser is used to prepare this, and then the microstructure provides, and you go down to the details, okay? So I give you another example. The old version saying the formation and the mathematical model of each geometry are analyzed and the models are verified by experiments. So what? It really doesn't tell me the details, right? And then talking about the cutting forces. And the new ones is basically you analyze it analytically, because lots of work, if you can do it analytically, it really leads to a good prediction and could be used for something else. So I think, if you try to condense it, make it, more, focus on what's new, that will make the paper more noticeable. And the conclusion needs to highlight what's new, okay? And do not just summarize the work, say I did A, B, C, D, but really try to give a perspective about what's new and also the future work, right? So with that, I think I'm going to just summarize, quality of the idea, quality of the writing, quality of the reviews, and I'm saying reference. Okay, those will be the key things, and hopefully will be beneficial. And then after that, you do the promote of your work.
The only
Okay.
point, yeah, the key message is that novelty has to be there everywhere.
Yes. Right.
You can't get away without that.
Yeah, that's the first part.
That's
Quality of the idea.
exactly. Mere description of the work will not help. Yeah. So
Right.
the one of the questions is that you have done the thermal model. So question is that which type of software you have used for developing the thermal model, and how to do the modeling of the deposition, like the melting and solidification.
Yeah, so what we did is, we just have the thermal model right there. And what we did is we actually created the element birth. So you know the two path already about the laser two path. So you know the deposition that's going to happen at this particular moment, and what's the energy. So it's going to be the heat input coming in. And for this part level simulation, we didn't model explicitly, say, powder melting in the melt pool, or that kind of specifics. There's another group, not my group actually. We are collaborating to more looking at the powder and the melt pool interactions at that level. So we basically use a part level, the small scale level, to validate the number of the things that we put into the part level, and so that we can simulate much faster way.
Yeah, I don't think any specific question is there in the chat box. If any, so the audience can quickly put one or two questions. Professor Cao, it's a wonderful, the research that your team is, doing, and thank you so much for enlightening us.
Well,
yeah.
Thank you, my pleasure.
I think no more question is there, so let us close today's session. Thank you so much once again for accepting our invitation and enlightening our students. And I think the students will also get the opportunity to work with you in future. So I request, I encourage the students to, think in that direction. I request Ananta to let us know about the last webinar series. Yeah, thank you. Yeah. Last webinar series, that will be on the next week. And then speaker is Professor Suman Chakraborty. Again, Professor Suman Chakraborty doesn't need any introduction. He is very famous all throughout the globe. So he'll be talking about the affordable healthcare equipment manufacturing. So that's a completely new, the domain. So how to come up with the affordable healthcare equipment? What should be the manufacturing steps? What are the difficulties of the manufacturing steps? With that, the next week lecture, we'll close this year-long webinar series. Thank you so much once again for your presence, and I look forward to your presence in the coming Saturday. If you have missed any previous lecture, you can also watch this through scanning the code. And yeah, so at the end of after completing the 52 webinar series, we'll also come up with a compendium. So where all the speakers, the abstract of the the webinars would also be documented. Thank you so much once again.
Thank you.
Thank you.